Imagine a world where your AI assistant doesn't have to wait for each word to finish before thinking of the next, where entire sentences, even complex code, are generated in a single breath. That's the promise of parallel token prediction, a breakthrough framework that shatters the long-standing bottleneck of autoregressive language models. For years, transformers have dominated AI by generating text one token at a time, each new word dependent on everything that came before. This sequential process, while powerful, is fundamentally slow. For long outputs, this means hundreds of forward passes, each adding latency. It's like writing a novel by typing one letter at a time, waiting for the cursor to move before pressing the next key. But what if you could predict multiple tokens at once, coherently, consistently, without sacrificing quality? That's exactly what parallel token prediction enables. It's not just faster, it's different. Instead of sampling tokens after the fact, PTP embeds the randomness itself into the model. Here's the key insight. When you sample a token from a probability distribution, you're using a random number, let's call it U, to pick the right word. That number contains all the information about which token will be selected. So why not feed U directly into the model? By doing so, the model learns to predict not just what the next token is, but how it depends on the random choices made earlier. This transforms the model from a passive predictor into an active, coordinated generator. We formalize this in two ways. First, one-hot PTP predicts the exact sequence of tokens in one call, collapsing the distribution into a single choice. It's fast, efficient, and perfect for deployment. But it loses access to the full probability distribution, making it hard to adjust temperature or quantify uncertainty. So we introduce Categorical PTP, which preserves the full conditional probability for each token. It conditions on all previous auxiliary variables, but not on its own. This means the model still sees the history, but remains uncertain about the current token, just like a real autoregressive model. The result? The same expressive power as traditional transformers, but with the ability to generate many tokens in parallel. And here's the math behind it. Theorem 1 proves that any future token can be predicted as a deterministic function of the context and a sequence of auxiliary variables. Theorem 2 shows that conditioning on past auxiliaries recovers the original autoregressive distribution. This means PTP isn't just faster, it's equivalent in representational power to autoregressive models. There's no trade-off in modeling capacity. Now, how do we train such a model? We have two powerful approaches. The first is distillation. Take an existing large model, say Vicuna 7b, and reverse engineer the auxiliary variables it used to generate its output. Then train a smaller PTP model to mimic those choices. The result? A lightweight model that generates multiple tokens per step, without losing fidelity. The second is inverse autoregressive training, which works without a teacher. We start from scratch, generate sequences, and iteratively determine the auxiliary variables that would produce them. It's like solving for the hidden randomness that led to a given output, using an invertible process similar to inverse autoregressive flows in continuous spaces. But even the best model can make mistakes. So we add error correction, a simple yet powerful verification step. The PTP model generates a batch of tokens. Then a verifier, either the teacher or the same model, checks each one using the same auxiliary variable. If it matches, we accept it. If not, we stop at the first mismatch and let the verifier correct it. This ensures correctness while maximizing speed. The results? State-of-the-art performance on SpecBench, a diverse benchmark of real-world tasks. On Vicuna 7b, our OPTP model accepts 4.18 tokens per step on average, a massive improvement over existing methods. And in code generation, we see 7 accepted tokens per step, far outpacing independent prediction models. Why does this work so well? Because unlike prior methods, PTP models dependencies between tokens. Independent prediction, where each token is guessed separately, leads to nonsense like def/sys or import find. The model has no idea what came before. But with PTP, the auxiliary variables coordinate the entire sequence. The model sees the context, the history, and the randomness, and generates a coherent, meaningful output in one call. We've tested this across domains, from taxi pickup prediction in New York City to complex coding challenges. In every case, PTP matches or exceeds autoregressive performance, while slashing latency. And the implications go beyond speed. This framework opens the door to true parallel generation, a new class of models that think in sequences, not steps. Future work could scale this to billion-parameter models, integrate it with multimodal systems, or combine it with speculative decoding for even greater gains. But most importantly, this proves that the sequential bottleneck in transformers isn't inherent. It's a design choice. And with PTP, we've shown that universal, efficient parallel generation is not just possible, it's within reach. So the next time you ask your AI to write a function, generate a story, or solve a problem, remember, it might not be waiting for each word. It might be generating them all at once. And that, my friends, is the future of language models.